going to do, this is something that came up, problem 6.7 in the book, 6.7 in the book is something that is not well, it's covered, but there's an easier way to solve it than to talk to one of the guys who want to go through that. All right. So for this problem, he defines an E field, and he has some E naught, what is it, 5? Right.
5 cosine pi times 10 to 6 t minus 3x
5 times 10 to the 6 t minus 3x.
plus 2y in the AZ direction.
All right, now this is one that's a little different, because inside the argument, you have both x and y variation, and it's not in the standard AX orientation, that was AZ, right? Now there's two ways to figure out what they want. They ultimately want H field, and they want the direction of propagation. They want that. All right, now, the way you can get this information requires an understanding of power flow first. So I'm going to do power flow, then I'm going to return to this, okay, everyone? Now, when we talk about power flow, in general, let me do it this way. I'm going to say E in general, the way we've been dealing with it, has some magnitude E naught, and in the phasor domain, it's e to the minus j beta z ax. It's a standard plane wave propagating in the plus z direction. That's the phasor form, right? The temporal form of this would be the same E naught, and then it would be a cosine of omega t minus beta z, and then it would be in the AX direction as well. Everybody follow me? That's time, that's phasor. Working class? You'll notice the variation is in Z only, right? It doesn't have an X and Y variation. Now, if you have this electric field propagating in the plus Z direction, the value of the H field here, you can get by saying it's equal to 1 over eta, or it would be eta of the region, and again, eta is the square root of j omega mu over sigma plus j omega epsilon. And in general, if you're talking about a lossless case, eta itself would be equal to simply the square root of mu over epsilon. And frankly, that's the square root of mu naught over epsilon naught times the square root of mu relative over epsilon relative, which is simply 120 pi times the square root of mu relative over epsilon relative. You all follow me in this class? I'm just trying to put some things up here I can reference. Everybody got that? All right, this is again something, when we look at this, we might as well do it for the lossless case, because that is lossless. If it would be lossy if there was an e to the minus alpha z in there, or alpha times those coordinates, all right? There's not. There's no e to the minus alpha, you know it's lossless. Everybody got that? So here, I get the H field by doing that. Then I take the vector, unit vector in the direction of propagation, and I cross it with E, and I get the H field. Are you with me, everyone? It's taking the E field, dividing by eta, that puts in terms of H. This is, well, I'll do this in a second. And here, I have 1 over eta, in this case, eta naught, if it's lossless. Then direction of propagation we get by inspecting this. So a vector, unit vector in the direction of propagation is simply AZ. Does everybody agree with that? I don't want to spend too much time on this if we all. How many see this right here? How do you get the direction of propagation? You all see it or not? You want to find the direction of waves propagating, right? You want a unit vector in that direction. Well, just look at this, right? This is going to be propagating in the Z direction, isn't it, class? How many see this? I'm not sure if I'm reading in the classroom. Does anybody not see this? It's hard for me to read the class. You don't see it?
No.
All right. You don't see it?
I have a different question. I see how to get it.
Oh, go ahead.
So, in a more general sense, say you have like a function of multiple variables.
Spatial variables.
Yeah. How would you get?
I'm getting to that. Thank you. I'm getting there. I first got to do the power thing, all right? Then we'll get there. Now, for this one, this would be 1 over eta naught, and then when I take AZ crossed into AX, right? I'm going to get AY, correct class? So now I have this as E naught right here, and it's going to be e to the minus j beta z, and it will be AY. Now this is the E field, the H field, and now we get the power. And this is going to be something where I'm going to write the power in terms of the instantaneous form and in terms of the phasor form. So when we talk about power, I'm going to refresh your memory about one thing. Back in the day when you took circuits or you took Dr. Gross for power or somebody like that, you had this, your general form for power, and power dissipated, that was equal to V of t times I of t. You also had forms like V of t magnitude squared over R if it was just a resistor. Do y'all remember that? Or you had a form where you had I of t squared times R if it was a resistor. Now, if you have impedances where you have real and imaginary parts, it gets a little different. But you all remember this basically, right? This is the instantaneous form. When you took power and you had the average form of power when you did circuit analysis, that was 1/2 the real part of V phasor, and it's times I conjugated. Y'all remember that? I conjugate, correct class? Now, we know for a resistor what this came down to, it was just 1/2 times simply V naught squared over R, or it was 1/2 I naught squared, right, times R if you had just a resistor. I'm just refreshing your memory with all this. So there was this standard form that reduced to this for the instantaneous, or for the average power part, right, for circuits. Y'all recall this right here, right? Now, with that in mind, I'm going to talk about power in general and then get to the specifics for this problem and its application. So in general, when we talk about power, this form of power is in watts. This form is in watts as well, right? When we talk about power, it will be in watts per meter squared. So our version of power, and this is called a pointing vector. The pointing vector has the symbol in Dr. Wentworth's book of P. A more common form you're going to find in the journals, right? And this is a power density. More common form you're going to see in S, and you'll have SAB. This is in all the journals. And this is a symbol for pointing vector, power density. And this is equal to, in the time domain, it's just equal to E of t, simply that crossed into H of t. And again, the units are watts per meter squared. Now that's the instantaneous form. You'll notice that E has the units of volts per meter. H has the units of amps per meter. A volt amp is a watt. Per meter is per meter squared. Watts per meter squared. Follow me on this, guys? It's exactly similar to this right here. That would be in watts too. Correct, class? Now, more on this. Now we go to the form that is most common and most general. It's the average form of power, and it's like average power flow, or average power when you're talking about circuits. There, I've got to define an E field. In general, the E field is some E naught, e to the minus alpha z, e to the minus j beta z. I'm going to keep to the standards that we've been doing. Propagating the z direction has a vector sense in the AX direction. So it's pointing AX, propagating in Z, and that again is volts per meter. That gives rise to an H field equal to H naught. Well, really, I'm going to put it in terms of E. E naught, right, divided by eta, and I want you to put the magnitude of eta here, and it's going to have, this would be E to the J, and that would be the angle associated with eta. Now remember, eta here in general is a complex number, so it generally has some magnitude, eta, and it's some angle, e to the j theta associated with eta, right? The angle that theta is at? The angle that's associated with eta. Eta has a real and imaginary part generally. You follow me? It's complex. Everybody got that? I hope I'm not in your way. Clear on this, guys? Keep watching this over here. Now, and these are vector phasors. I don't keep putting that on there because it's obvious when you have AX, it's a vector. When you have a minus J beta Z, it's phasor. Yes, sir?
For the magnetic field, what was the exponent on that?
I'm not done with it yet.
Oh.
It's going to be e to the minus alpha Z times e to the minus J beta Z. Now, bear with me here for a second. Is there an eraser on that? I'm looking straight up, but not having. Okay. All right, now, people, watch this and just pay attention. Here, this is the magnitude of eta, that's the phase of eta, right? How many realize when I take 1 over e to the j theta n and take it to the numerator, that becomes minus j theta n? Everybody got that? So I'm gonna do that. I'm just simply rearranging this. Agreed, class? Now, the formula that I put up there, or that I'm gonna put up there, is gonna require the conjugate of this. Why don't I put it down here? So then the power, now this is gonna be power density, all right, in a phasor form, or really, it's average power density, equal to S av, but now it's average. And that's equal to 1/2 the real part of E crossed into H conjugated. And that's in watts per meter squared. Follow me? Now that's just like this formula, only it's a vector form, all right? This is volt amps. This is volts per meter, amps per meter. So it's volt amps per meter squared. Follow me on this, class? Can you all see this over here? I'm sorry if I'm blocking. Yell at me if I'm in your way. Now keep paying attention to this. I need the conjugate of H, right? In order for us to do this. Well, when I conjugate that, what does it do? It simply takes the angles, and if they are negative, makes them positive. If they are positive, makes them negative. Correct, class? You all with me? So I'm gonna conjugate it. It means I get rid of that negative symbol right there, and that negative symbol right there. Follow me? Everybody see this? I'm trying to make the best use of this time. Just gotta make sure you see these little things. Now I'm gonna go ahead and do this right here. So that means P average right here, or S average, will be equal to 1/2 the real part, and then it's E, and that's my E field, E naught, e to the minus alpha Z, e to the minus J beta Z, AX, and it's crossed into the H field. Well, the H field, that's a cross product operator. The H field is going to be equal to E naught over magnitude of eta. Remember, it's the magnitude, no phase angle there. And then it's going to be times E to the minus alpha Z times e to the plus J beta Z times e to the J theta associated with eta. I've just simply recopied that stuff into the formula. Got me? Now watch, you'll see how a lot of stuff disappears in a second. When I look for you for a second, in order to get rid of the complexity, first you see how e to the minus J beta Z times e to the plus J beta Z gives you 1. You all agree with that? Class, right? So I want to get rid of that. Now do you all see how AX crossed into, should be AY here, but I didn't put it down. AX crossed AY will be AZ, and I'm going to take that out. With me? Everybody? Now that I have that, I've got AZ here, and I've got this cross operator now I can get rid of. Now, E naught is strictly, the E field's strictly real, 5, 10, 100, something like that, right? That's an E naught again, so it's got an E naught squared. The magnitude of eta is strictly real. Do you all agree with that? E to the minus alpha Z, if alpha is a real number, is strict real. It's like e to the minus 2. It's a real number. The only imaginary number is right there, e to the J theta n, right? And the real part of that would be what? If you have e to the J theta in general, it's what? Cosine of theta plus J sine of theta. What is the real part? Cosine of theta n. So this whole equation becomes simply P av here equals 1/2 magnitude of E naught squared over magnitude of eta times e to the minus 2 alpha z. The reason it's e to the minus 2 alpha z is there's two of them. Are you with me? So it becomes e to the minus 2 alpha z. And then I have cosine of theta n in the a z direction. And that's the power flow if we're talking about power density, watts per meter squared. We're talking about a wave oriented in the x direction, propagating in the z direction through a media that has a complex intrinsic impedance of eta, and it has the corresponding alpha and beta too. All right, you'll notice here there's no imaginary part to that, it's strict real. You'll notice that it decays as e to the minus 2 alpha z, and this is the general form. Now, if it's lossless, and this is nice, write this down, lossless, or it means sigma equals 0, alpha equals 0. If it's lossless, then the average power density is simply equal to magnitude of E naught squared over 2 eta, magnitude of eta. If it's lossless, this goes away because e to the 0 is 1, and the cosine of the angle, if it's lossless here, will be 0 cosine of 0 is 1. You agree with me, everyone? So you get this, and it will be AZ, and that's watts per meter squared. Now, the reason I'm making a point about this, if it's lossless, all right, a lossless region, you take the E field, if you want the power density, take the E field, square it, and divide it by 2 times the magnitude of eta, and eta will be a strict real number. And that's it. That's all you have to do. With me, class? Now, I said that, and I'm going to get back to this. Now, here's what Dr. Whitmore's solution says about this. They get this, direction of propagation, by taking the power density, E crossed H, and here I'm going to make mention of something. That's not the only thing you do. Anytime you want to know the relationship between EH and the power density, E crossed H is the direction of power flow. With me? So if you have an E field, and you know the direction is propagating, simply take the E field, use your right hand, take your thumb, put it in the direction of propagation, and take the E field, and then go through the smallest angle, cross it into the H field. In other words, don't revolve this way. You cross a small angle into the H field, that's the direction of propagation. So for instance, if I was propagating towards you, and it had an E field in this direction, and an H field in this direction, right? Or E field, let me do E field in that direction, H field in that direction. E cross H, direction of propagation is the way it would work. If I have E and H in general, if I take E and cross H through the smallest angle, that's between 0 and 90, all right, into H, that gives me the direction of propagation. Follow me? And that's as simple as it gets. Now, for this one, he says, I take this, well, that's a magnitude, right? It has both direction and it's got direction and magnitude. And divide by the magnitude of E cross H. That's what he has in his solutions manual. Does anybody remember this problem looking at this? What is the problem with that? It implies that you know how to get H, right? He doesn't specify how to get H. That's what I'm about to do. Now, the more general form for the E field in propagating in free space when it's a plane wave is this. E will be equal to some E naught. I'm going to do the lossless case too. I don't want to mess around with loss. Times the cosine. And then it will be, actually, let me do the phasor form. It'd be better I put phasor. It's e to the minus j, and now it's going to be something called k vector, or beta vector in our case. B vector dot r vector. And I'm going to say it's polarized in the AX direction for now, but it doesn't matter the direction. Do you follow me? You have to know the direction is polarized, and that you can't get unless it's specified. Well, you could. Every time I say that, I think, this will be specified, the direction of propagation. Now, in general, R is this. Just write this down. R is simply x, ax, this is in Cartesians, plus y, ay, plus z, az. It means it's simply got the component x, y, and z in front of the unit vector associated with it. Beta in general is beta x ax plus beta y ay plus beta z az. Now, if you think about the case where you have propagation only in the x direction, in the z direction, are you with me listening now? Then, if you took beta, where you had only beta x ax, because then these two would be 0, and you dotted it in with this, x ax plus y ay plus z az, you'll notice how you would just get beta x, I'm saying it's propagating the x direction, how about z direction? We'll go back to that. Put beta z az. You would simply get beta z times z. Y'all follow me on that, class? If you have this, in general, beta and r are vectors, right? But suppose you have propagation only in the z direction. Follow me? Then these two would be 0, right? So it'd be beta z az dotted into this. Well, az dotted into ax and ay is 0, az into az is 1, right? So then you just get minus j beta x times, beta z times z. Do you follow me on this, class? Give me a show of hands if you see what I'm talking about. This is the general way you write it. Now for our case, what do we have? Back here, don't worry about this because you're not going to get anywhere doing it that way. That is correct statement, but you have to get H. When I look at this right here, how would this be associated with a propagating wave? Well, that would still be E naught, right? And it would be cosine of omega t minus beta vector dot r vector. I got ax there, but a woman. You follow me in this, class? Now look at what he does. This is his beta dot r right there. Do you all see that? He doesn't have this in the book. That's the reason I'm spending a little more time on this. Now if you look at this, what is it? Well, actually, the way I showed you, there's a minus beta, and there's a minus beta there too. So I see that what I have here is the beta dot r is equal to 3x plus or minus 2y, if you look at that. Do you all see that, class? Because there's a minus in front of there. There has to be a minus beta dot r, right? So I take the minus out in front. Well, that means I got 3x and 2y. With me? Now the simple thing is this. The coefficient of x is beta x, and the coefficient of y is beta y. That's as easy as it gets to remember. With me? That's it. So if I look at this, now I'm about to tell you how to get the direction of propagation. When I look at this, I can see I have beta x and beta y given, or I can say my beta vector is equal to, it's usually, by the way, if you're looking at other books and references, almost always the symbol small k is used for this, the wave number. It's not beta. In our book, we use beta. They're identical. Just remember, if you're looking on the internet for other sources of information, the letter K is universally used for that, almost everywhere. So now I have my vector beta here in general would be equal to 3ax minus 2ay. Now box that. That is beta in general. The magnitude of beta, the actual value of beta that has to do with the amount of maximum radians per meter that it changes in the direction of propagation, is equal to the square root of beta x plus beta y, or here it would be simply equal to the square root of 9 plus 4, right? And that's going to be 13. So that's the magnitude of beta, and that's the maximum rate of change in radians per meter that the wave changes in the direction of propagation. Follow me on this? These are the components of beta. Now to find a vector, a unit vector in the direction of propagation, what you do is this. Please write this down. You simply take b vector divided by magnitude of b, and that's the way to get it. Can everybody understand this, people? So for our case, it's simply going to be what? Our vector, a unit vector in the direction of propagation for this one is simply going to be equal to 3ax minus 2ay divided by the magnitude of that, or square root of 13. Does everybody see that? I said a lot there. Some of you have just cut right to the chase and said, you mean, when I look at this thing, the only thing I need to do is say, take a minus sign in front of whatever the spatial things are, whatever's left, the coefficient of x is beta x, coefficient of y is beta y, right? You can all see when I take a minus sign out in front, if I did that right, if I put parentheses there, this would be minus 2y. Follow me on this, class? How many see this right here? That's the easy way, just looking at it that way. I wanted to show you a more, I guess, developed treatment where technically they usually do this. They talk about R, N, beta, or K as vectors that are dot, where the dot product is the thing that results is the argument in here. All right? That's the only thing I'm doing, but this is a more complete definition. Now, so that, this one, that's the unit vector and the direction of propagation. What else did they want? H, well, now for H, we can get this. How about we do it this way? All right. So the unit vector in the direction of propagation was equal to 3ax minus 2ay over the square root of 13, right? Now, we can rewrite this. Y'all take a look at this right here. I can rewrite that in the phasor domain as E is equal to 5, right? E to the minus j, and then it's going to be 3ax, or sorry, 3x, and I can have e to the minus or plus j 2y az. Y'all see I just broke that up? I could put e to the minus j quantity 3x plus 2y, close quantity, but I broke it into two separate parts. Do y'all see this, class? Now when we have this, there's two ways of getting h out of there. I want to just tell you, I'm going to show you the easy way in a second. This is the hard way. You could say the curl of h, in this case, since it's lossless, then sigma 0, it would be an e to the minus alpha z, or alpha, whatever that is, if there was attenuation, but there is none. So we know sigma 0 is equal to simply j omega epsilon e, right? Well, that's true there, and we also know the curl of E is equal to minus j omega mu times h, right? So if we want the h field, and I think he does it this way in his book, which is not really a good way to go, you can find h as 1 over minus j omega mu times curl of E, and you can get h that way. But you're going to take derivatives. Follow me, you put a matrix up there and determine it, and that will get you it. Are you with me? It'll get you h, absolutely. And then once you have that, you could default to, if you want the unit vector, you could say it's E cross H over the magnitude of E cross H. And that would be a unit vector in the direction of propagation, but it's easier to do it the way I showed you. And simply say that now, if that's the E field right here, the phasor domain E field, we can get the H field by saying it's 1 over eta, and I guess he didn't, does he give you anything about eta in there at all? Anything about the frequency? Well, he gives you the frequency, right? Well, we know the magnitude of beta is this, so we can get, I'm gonna regret doing this. We know it's lossless, so we know eta is equal to square root of mu over epsilon, and we know that, let's see, beta is equal to the square root, or is equal to omega times square root of omega, or of a mu epsilon. And that means, well, we could probably go down this road and solve for mu and epsilon, because we have the ratio of E magnitude to H magnitude here, and that is magnitude of eta. Right here, I'm just going to do it this way. We can take this over 1 over eta times unit vector in the direction of propagation crossed into E. We have E, it's only in the Z direction, and we have this in terms of, where is it? This, and we can do that cross product. I'm not going to belabor this point, but there's more than one ways to get it. I prefer to get the direction of propagation just looking at the actual functional form here. That's my take on this, all right? I'm not going to do the curl of H, or the curl of E, and take that, divide by minus j omega mu to get H, and then find the vector by saying I know that E cross H is a vector, and it's going to have a direction of propagation. It's going to have, the vector will be in the direction of propagation. I'm not going to bother with that. It takes too long. But Dr. Wentworth probably wants you to realize that. That's what I would do. Now, let me get back to what I was saying on this one, on the other side. I worked that problem out in detail afterwards, but I've got stuff to cover today. All right, I covered the power. Are there any questions about the homework at all?
Did you put a third homework? We didn't get a third homework. I was afraid.
That's on me. The other class didn't either. It won't happen again. But do you have any questions of the prior homeworks? Because I gave you things that we didn't actually cover in class in that homework. Right? Any questions at all about them? This is one of those. That's a good problem. Which one?
619.
Yeah, you're saying 619, right?
Yeah. Just tell me what it is. 6 point what?
19.
690. Is everybody able to view the video? How many have tried? Can you see it okay? Okay. All right, what is 619? And seawater. Give me the specs on this.
Epsilon relative of seawater is 72 and sigma is 5.
Uh-huh. Go ahead.
So you got, wait, this is 19?
Yeah.
Yeah. So yeah, E is equal to 20,
E equals 20 what? Cosine?
E to the negative AZ, alpha AZ.
Minus, e to the minus alpha AZ? Alpha?
Alpha Z.
Okay, e to the minus alpha Z. Go ahead.
Cosine 2 pi times 10 to the 6 T minus beta Z plus 5 the y direction.
Plus 5 here?
Yes.
And with AY?
0.5.
0.5. Plus 0.5. In the AY direction. What does it ask?
Assuming that epsilon to the third to the second power equals 0, find alpha and beta.
Oh, wait, it says epsilon double prime equals 0?
Yes, sir.
All right, that's because that's the complex permittivity where that would be the lossy part of it. It's 0, so there's not a lossy part to the permittivity. Go ahead.
And it says find alpha and beta and the instantaneous form of H.
All right, so they want alpha, beta, and H of T. All right, for these things, did he say it's non-magnetic? You should. Mu relative is 1. Seawater is non-magnetic.
Yeah, it's a mu r equals 1.
Mu relative equals 1. Well, we can take one look at this, and let's go through what we need. When I take a look at this, let's go ahead and dissect it. First, how many see that this is propagating in the plus Z direction? Just show me your hands, all right, so I can make sure. Y'all see it? Alright? The direction of propagation is AZ. Next thing I'm gonna look at is omega. What is omega by looking at that? It's the coefficient of t inside the cosine argument, isn't it, class? So omega for this one is 2 pi times 10 to the 6th. And that means f is simply equal to what? 10 to the 6th hertz, or it's a megahertz. Do y'all follow me? This is what you need to do by looking at that waveform. Got me on this, everyone? Next, after we have that, we want to get alpha. Well, alpha is gamma. Gamma is equal to alpha plus j beta, right? And what's the form of this in terms of the parameters, people? And in terms of the constituent parameters? Well, it's the square root of j omega mu times sigma plus j omega epsilon, isn't it? By definition, correct? Now this is where your calculators are saviors. So now I've got omega, I've got the equation, so I can say that gamma equals alpha plus j beta equals the square root of j times omega, which is 2 pi times 10 to the 6th, right? Then I have sigma, which is given as 5, plus j omega epsilon relative, which is 72, times epsilon naught. And remember, epsilon naught is really equal to 8.854 times 10 to the minus 11th, that's farads per meter, or 1 over 36 pi times 10 to the minus 9th. And I don't care which one you use, just know it, all right? Gotta know this one. And I just left it as epsilon naught there. That's alpha plus j beta. Can somebody use a calculator and give me that? Because I'm not gonna play with that in my head. I had a professor that used to be able to do this stuff on slide rules and it blew me away. I mean, he could do it faster than I could type it in my calculator. You got 2 pi 10 to the 6 times 5 times the quantity 5 plus j, and omega, by the way, is this. I didn't put the omega in, it's this. Right?
Alpha and beta are about 4.4.
They're both the same? Did you calculate it? All right, give it to me again, 4.4?
Yes.
That's it?
Well, alpha was 4.3999.
4.4 is good. All right, if that's the case, we have alpha and beta, right? Now we need one other thing. We need eta, don't we? We need the intrinsic impedance of the meter, right? So now we have to put down the square root of j omega, and I'm leaving omega up here, times mu, which is just mu naught, over sigma, which is 5, right? Plus j omega times 72 times epsilon naught, right? And by the way, mu naught is 4 pi times 10 to the minus 7th, and that's henries per meter. You should, after you do a number of problems, mu naught, epsilon naught, c the speed of light, those will be burned in your brain. You're not gonna have to look them up. Just by the number of problems you're gonna be doing. Are you with me on this, class? What do you get for this? Now, you're gonna get probably a number where you have the real and imaginary about the same, but just give me a magnitude and the angle will be about 45 degrees. Anybody? You have very good calculators. You can do this very quickly. You got a Surface Pro, it looks like, or something like that. You can probably do it in MathCAD or something.
Yeah, I'm trying to write everything down now.
Yeah, go ahead. If I'm going too fast, yell at me. Anybody got a calculator to punch this in for me? What is that?
This iPad.
A lot of people like I has for this kind of stuff, notes.
On the alpha side.
People on
Yeah,
the
you just
sample.
he didn't put me
A lot of, I mean, they use either MacBook or iPads for everything.
Right off the This thing's dead. Does anyone have a different?
Remember, omega you could probably enter in, 4 pi times 10 to the 6. Mu naught is 4 pi times 10 to the minus 7.
Alright.
Anyone?
I'm trying to tell you.
Yeah.
1.257.
1.257 e to the, is it 45 degrees?
Yep.
E to the j, 45 degrees. The real and imaginary are about the same. You can check that and see if it's right, but I believe you on that one. it's gonna be, whenever you get something that's very lossy, it's a good conductor, then you're gonna get the real and imaginary parts of both gamma and eta the same. It'll be at 45 degrees. Got me, guys? All right, now when I have that, I got my direction of propagation. I'll put E in a phasor form. Now, this is the thing you gotta watch for right here. If I put E in the phasor form, you see this 0.5? That tends to be there just to make your mind stress a little. This in the phasor form will be equal to simply magnitude of 20, still E to the minus. Now you have alpha, right, wherever it was, 4.4. This is alpha, I didn't put it down. And this is beta. So E to the minus J, E to the minus 4.4 Z, and then it's going to be times E to the minus J, beta is 4.4, right? 4.4 Z minus 0.5. The reason I put a minus there is because, remember, this is minus J beta Z, right here, and this needs a minus, so when this times this goes through, it becomes plus. Follow me, guys? Everybody see that? Gotta make sure. If I'm blocking anybody, tell me to get out of the way. And that would be in the AY direction. Now that's the phasor form of E that we're gonna use to get the rest of it. Now we come over here, and if we want H, we default to 1 over eta, unit vector in the direction of propagation crossed into E. All right? Here, H becomes 1 over magnitude of eta, and I'm gonna put 1 over the magnitude of eta, which is 1 over 1.25, and it would be E to the J 45 degrees here. Unit vector in the direction of propagation is just AZ. Crossed into the E field, and the E field is 20 times E to the minus 4.4 Z times E to the minus J 4.4 Z minus 0.5, and that's in the AY direction. So when we do this, we find H equals, first thing I'm going to do is take 20 out in front. I'll take 1.25 out there too. We'll do that math in a second. Then I have AZ cross AY is going to be equal to minus AX. Right? Minus AX, and this is going to be, next I'll put down the E to the minus 4.4Z, and then E to the minus J 4.4 minus 0.5, but I want to say one thing. When I take E to the J 45 upstairs, it becomes E to the minus J 45, correct, class? So now what I can do is you just put down, and this is the thing that bugs me. See, he doesn't specify these are radians, but I know they are, right? The arguments in there are radians. The Emag2 is in radians, almost universally. So instead of 45 degrees here, what I really should put down is going to be pi over 4. That would be in radians. Follow me? I'm glad I did it. That's a mistake I see. So up here, that's going to be equal to, this would be E to the minus J 45 for pi over 4 radians. So then you would add plus pi over 4 here. And that would be in the minus A extra, and that would be amps per meter. And that would be the H field. Now that's the H field in the phasor domain. Do y'all follow me? Not in the time domain. That's in the phasor domain. Now, I mean, I can leave it like this. When you have a minus here, here's one trick. You can always add or subtract pi inside that argument to get rid of the minus. Anytime you add 180 degrees to a phasor term, you flip the sign. If it's negative, it's positive. If it was positive, it becomes negative. Follow me? Now, I don't know if Whitmore's book did that or not, but we could do that. I'm going to leave it like this for now. Okay, class? but there's a minus sign there. So that means h in the time domain, if I leave the minus sign, would be minus 20 over 1.25. And that's going to be e to the minus 4.4z. And then I'm going to have cosine of omega, that 2 pi times 10 to the 6, p, minus, and then this, minus 4, this should have been z right here. It should have been minus 4.4z, for somehow I missed it. It's going to be minus j 4.4z plus 0.5 plus pi over 4. And that would be in the AX direction. Now, if Dr. Wentworth's book doesn't have that as minus, then you have to add a pi in here. But that's what it's going to be. And you can add these numbers together, the 0.5 plus pi over 4. Does he have that? Anybody got the? Who has this?
Why is it pi over 4 not minus pi over 4?
Well, here, let me just, you know what, you're right. That's my bad. I try to make that a minus 0.5 plus that, so this times this would end up minus. And so that would be a minus pi over 4, my bad. Whoever caught me on that one, thank you. Does he have a solution? Is that what it is, or? Look in the front, does he have a minus out here or not?
Yeah, he does.
Okay, then that's it. But he probably added these numbers together, 0.5 minus pi over 4.
Yeah, he had those. And last one's minus.
That's 16.
What?
Minus 16 degrees.
Well, if that's the bad thing. You put degrees in with radians, it makes no sense. It shouldn't, it should be radians in there.
It has degrees in there.
It shouldn't be. That's a mistake. All right. But that's right, and that's how you do it. Was there another part to that problem or not?
I think
That's all?
Okay. You asked that. Did you have another one? It's good to do these, oh gosh, but almost out of time, but let me, that's all right. Working problems actually kills a lot of, it gets rid of a lot of uncertainty, so I like doing that. Let me just tell you what I'm going to do. Next time is going to be polarization, and let me tell you one thing about polarization just before I get out of here, because I know I'm out of time. When they talk about electric field polarization, it becomes very, very important for a reason. Because based on a polarization, when you send a signal, you're going to get polarization that's opposite back if it has to do with a circular elliptical polarization. Now, briefly, your electrical engineers are smart. When they talk about a linear polarized wave, it means the electric field never changes its sense of orientation, only the magnitude. So if I'm sitting here and I've got an antenna and I'm measuring the electric field, it's either up or down if it's vertically polarized. If it's horizontally polarized, the electric field's in this direction, whatever that be. Follow me? Never changes its orientation, just magnitude. When you talk about circular polarization, the electric field magnitude never changes, it just rotates in a circle. And if it rotates one way, called right-hand circular, and you send it with a right-hand circular polarization, that's how you tell right hand. Take your right hand, put your thumb in the direction of propagation, take your finger, and then make it go clockwise from the way I'm looking. If it goes that way, that's right-hand circular polarization. If it goes the other way, it's left-hand circular polarization. Pretty easy. But if you send out a right-hand circular polarized wave and it strikes a conducting body like an aircraft, it'll reflect back left-hand. And you can make a left-hand polarized filter, so you filter out all the garbage but the reflected signal for radar processing, and that's very, very useful, and that's what I do. I do radar. And I'll get to more of that next time. I am going to put up some problems. Sorry we didn't get more done, but I'd rather get that done. We don't have a class.